Hello and welcome to lesson 3 of week 12. In this lesson, we're going to look at the Bellman-Ford algorithm, and this algorithm is used when we have negative weights. Now, it is a graph algorithm that finds the shortest path from a single source to all other vertices in a weighted graph. So when we use the Dijkstra's algorithm, we can supply negative weights, but this helps with negative weights. But there is a problem with negative sec where the total weight adds up to a number that is less than 0. And this means that the total path cost will keep decreasing forever, will have infinity. And so we want to implement this, keeping that in mind. The whole intuition behind the algorithm is based on relaxation. And when we say relaxation, we try to make the shortest distance smaller each time through the edges. Now, because the longest possible single path in a graph has v-1 edges, if a shortest path exists, then it must be found within v-1 iterations. And we do one more loop to check for negative sec. So what we do is to set the distance of all nodes to infinity. That's the first step. The second step will set the distance of the start node to 0. We will now say for I is equal to 1 to v-1 or the vertex minus 1 for each of the edge. So that is for the vertex 1, vertex 2, the weight. If the distance plus the weight of a vertex is less than that, the distance of the other vertex, then we want to update, right? Then we check for negative sec. Now when we implement this, we're also going to have a way we can perform relaxation and optimize the code. And so that we don't waste time, we go straight into optimizing this code, and while we build it once and for all, and know that there are other ways you can do it. Now the real world case scenario for this is for GPS navigation with penalties, right? We have network routing protocol, we also have currency exchange and airline route optimization. So let's use early stopping for this while we implement it. And for early stopping, when we create this code, we're going to add a flag to detect if there's no update in an iteration, or if the edge was relaxed, we break the loop early, something like that. So let's create the Bellman algorithm. I'll put it here. Def, I'll call it Bellman-Ford, and we want to start from a given node to all other nodes. Let's use the same thing. Distances is equal to v float infinity in for v in self dot vertices. Right? So distances start equal to 0. For I in range, so we want to say the length of the vertices minus 1. So for I in range len self dot vertices minus 1, then we're going to have updated, we'll set this to false. Then we're going to say for u v w in self dot edges, if distance is u is not equal to float in and distance is u plus w is less than distance is v, then we'll say distance is v is equal to distance is u plus w, and we'll set update to true. Now, if not updated, then let's read early stop at iteration I plus 1, and then we can break. So this is how we can optimize this to break. And if we want to detect negative circle, we can now say for u v w in cell edges, then if distance is u is not equal to float infinity and distance is u plus w is less than distance is v, then we'll print negative weight circle detected, and you return none. Here now we can now return the distances. So this is how we'll implement the Bellman-Ford algorithm to be able to handle negative weight. So because this traditional one uses an edge list, but we can improve the constant time performance by using an adjacency list and only relax it from reachable node. This will now help us to reduce the number of wasted checks on the vertices that are not reachable. And so we can implement that. So this is optimized, but not as optimized as we will want it. And when you attend the live web conference on Saturday, you will see an optimized version, and we'll discuss this in details where you have a much deeper understanding. In our last lesson for this week, we are going to look at a real-world lab that will help us to understand this better by attempting to create a package delivery routing system for a delivery company that manages packages between warehouses. This is where we end this lesson. Thank you, and see you in the next lesson.